All right, F425. So here we go on our next lecture. So in the last lecture, we were talking about the criteria for the initiation of crown fire, right? So basically, how do we predict the transition from a surface fire up into tree crowns? So now we're going to talk about basically the second half of Van Wagner's 77 paper, where he discusses and presents some equations for understanding the criteria for crown fire spread, right? So once it's initiated up there in the crowns, can we get kind of horizontal tree to tree crown fire spread? Right. So the initial transition from the surface up to the crowns is really all about vertical heat transfer, right? And as we saw, it's really just based on the intensity of the surface fire, and then how far away are those crown fuels from the surface, right? So characterized by our crown base height at the stand level. So once we've determined yes, transition is likely to occur. Now we need to start thinking about, okay, well, how's this heat going to transfer horizontally, and will it be able to transition into a true propagating crown fire like the one we see there on the right? Once again, that picture is from the International Crown Fire Modeling Experiment, but just a really nice picture of a fully developed, active crown fire where we've obviously got the initiation, and now we're spreading horizontally from tree to tree across the forest. So before we get into Van Wagner, just a quick little overview here of some common terms used to describe different types of crown fire behavior. Right, so our passive crown fire is when we've got just individuals, maybe some groups of trees torching. But tree to tree spread, right, horizontal transition of fire from one tree to the other, either doesn't occur or is occurring on a pretty limited basis. And that tree to tree portion of the fire isn't really impacting the forward spread rate. It's still really about the surface fire, and then we're getting some trees kind of torching as that surface fire moves along. And then once we get up into active crown fire, and that's really what we're going to be thinking about predicting today, is when will we get active crown fire? That is where surface and crown fire are really acting as a single unit. And the energy from the surface fire is required to continue that crown fire, but the crown fire proportion or portion of the fire is contributing a lot to our spread rate. And the fire is really a sort of continuous wall from the surface up all the way up above the tree crowns. And once we've switched into this active crown fire phase, you'll pretty commonly see increases in spread rate that are pretty significant, right? Up to 3 or even 4 times faster spread rates than it would be were that fire a surface fire or even maybe a passive crown fire where things aren't quite as active and intense. And there's this other category that is often listed, and it's called independent crown fire, right? And that would be where the fire is just burning in the crowns, and there's no associated surface components. Basically, if there were enough crown fuels, or you're on a really steep slope or strong winds, that fire could just push from tree to tree without any surface fire, any additional heat from the surface. There's maybe a couple of limited documentations of this truly occurring, but it's when it does occur, it's probably a pretty transient, right, short-lasting occurrence. So maybe not super, or actually probably definitely not super important for our prediction of crown fire behavior, just because it's a really rare thing. And we'll see later on how it's sort of just it pops out of the math as sort of a possible outcome depending on your fuel and environmental conditions, but not something we're going to think too much about just because it's pretty rare occurrence. So those are our generic types of crown fire. So now let's just think about this as a theory of crown fire spread. So as we spent a lot of the earlier part of our semester talking about this theory for surface fire spread, right, where the rate of the spread of our surface fire is really dictated by how much heat flux are the fuel particles ahead of that fire line receiving, and then how much heat is actually required to ignite those fuels, right? And then so as we increase either the heat flux or we decrease the heat required for fuel ignition, that fire is able to spread faster. And so basically Van Wagner kind of took this same concept and wanted to apply it to crown fires, right? To predict, ultimately what we're going to see right now is a prediction of whether or not active crown fire is even really possible given our fire behavior and our fuel conditions. But so yeah, so based on this theory, Van Wagner put together this equation here, RDH equals E. Basically, it's saying the rate of spread times the effective bulk density, right? So effective bulk density just being the crown fuels that are actually available to be consumed, right? So included in the effective bulk density is usually just the needles and maybe some portion of the really small branches, but the larger branch wood and the tree boles and all of that mass isn't really considered as part of this equation because that stuff tends not to burn even in our hottest crown fires, and when it does burn, it's probably occurring after the fire front is passed, similar to the smoldering of large logs down on the surface. So we're just thinking about the effective effective crown bulk density, and then our heat of ignition, right? How much energy does it take to ignite that fuel? And so those three things need to basically equal the heat flux required for the propagation, right? You need enough heat flux to maintain that active rate of spread. Right? So when written in this form, that heat flux is really a critical value, right? The critical meaning that if it's not high enough, the fire is not going to spread. So you could think about E here being basically the minimum heat flux or energy flux required for the crown to continue to spread, right? Given our values of both the spread rate and the amount of fuel up there in the canopy. Right. So I just want to note here, right, that this equation is still in the same form as our theory of rate of spread. It's just Van Wagner has it arranged slightly differently, but we could rearrange it such that rate of spread is over there by itself, right? And now this looks very similar to our surface fire spread rate theory, right? So rate of spread equals the energy flux to the fuel over the heat required for ignition, right? So in this case, it's basically the amount of fuel times its heat of ignition. And so there you go. Just to see that this is really the same theory. He just has it arranged a little bit differently, and as we move through this, you'll see why he started in that form. Basically, because we're going somewhere a little bit differently here, where rather than trying to predict rate of spread at the moment, the first thing we need to do is actually determine if crown fire spread is even possible. So yeah, as we move through, we'll kind of see how that works out. So then I also wanted to work through the units. You guys have seen me do this before. I find it really helpful to think about these equations in terms of what the actual units are, right? It's kind of helpful for me to understand what this is really saying. So anyway, so here's our base equation, our RDH equals E. So the rate of spread is in meters per second times our crown bulk density in kilograms per cubic meter, and then times the heat of ignition for that crown fuel in kilojoules per kilogram. So when we go ahead and multiply those three things together, right, we can cancel out some units. So our meters get canceled out, our cubic meters turn into square meters, and then our actual fuel mass also ends up getting canceled out, leaving us with our E, which has units of kilojoules per square meter per second, right, which we can also just rewrite as kilowatts per square meter, right, so kilojoules per second per square meter. Right, so basically what this is showing us is that E is the required heat flux per per unit area in the canopy that's basically required to sustain this propagation, right? If E is not high enough, then it won't be able to maintain itself as a crown fire and will drop back down onto the surface. And so this area here is actually the vertical plane through the canopy space, not the horizontal plane down on the surface like we've seen in our heat release rate per unit area or fire heat release rate. With surface fire, we're now thinking about the canopy as sort of this just two-dimensional vertical plane through the canopy space, and we basically need enough horizontal heat flux into that plane in order for it to continue to propagate. So hopefully that visual there helps you out. But this is really what we're thinking about. We've kind of flipped our dimensions here from our discussions on surface fire. Okay, so what does this suggest, right? So we're trying to figure out whether or not it's even possible for us to have this horizontal active fire behavior like we see down in the image. And so basically what this equation is telling us is that the fire spread is only going to be possible if the rate of spread is fast enough, right? So rate of spread is really closely related to our intensity and basically how much heat is going to be coming off or how much energy is released by that fire. So if the rate of spread is too slow, then the fuel gets consumed too slow, and then there's not enough energy in the system to keep that fire in the crowns. Or we can have too little crown fuel, right? If the trees are really sparse, there's basically just not enough crown fuel to generate that required E, right? That required energy to maintain our active fire spread. So basically there's this balance between the speed at which it's moving and how much fuel it's consuming, right? Or basically the heat generated versus the heat required to ignite the next fuel element, right? Noticing that's our basic theory of fire spread, right? Our energy flux needs to be greater than the heat required to ignite the next fuel element. Otherwise, our spread process is going to fail. So based on that, Van Wagner wants to start rearranging this basically into a form that he's able to solve, right? We don't actually really know what E is yet. So anyway, the first step here is he's rearranging the equation so that our two sort of critical factors, right, our rate of spread and our amount of fuel are on their own. So we have RD equals the energy over the heat of ignition now. And then he's going to introduce in this new term called S. S is basically the mass flow rate, so how much mass is moving through that vertical plane in the crown space every second. And we can actually replace the E and H in our equation with this new idea of S, right? The mass flow rate. All right, so now we have we basically define this new critical value, right? This new value at which we can determine whether active crown fire behavior is possible. Right? I mean, if you think about this, it makes a lot of sense, right? If our crown space is really, really sparse, it doesn't matter how fast the fire is spreading, or at least within any sort of physical realism. It's just not going to be possible to get a fire to spread from tree to tree once you get down to a certain spacing or basically a certain bulk density in the stand. We just can't spread tree to tree. And this really makes a lot of theoretical sense. It's the basis for some of these aggressive treatments we'll do. So if you see in this photo here, right, and that red circle there is this treated stand, and it's pretty easy to see here, like with how far apart those trees are, there's just not enough bulk density there, right, to maintain a continuous active crown fire because of that spacing. But that doesn't mean that passive crown fire couldn't happen. We could still have 100% crown mortality in there, if the surface fire intensity were high enough, right, to torch out every single one of those trees, but we're just not going to get active spread because the trees are separated apart far enough. And then here's just kind of another example of that. This is kind of a nice picture of, and now I'm spacing on which fire this is from, but anyway, the fire kind of came over that mountain down and is coming downhill. Actually, is a pretty intense crown fire. You can see all those crowns were scorched out, and that was a fully developed active crown fire. And then the fire enters this fuel treatment zone, basically where they had done some work to thin out tree densities and also reduce the overall surface fuel load. And basically that crown thinning was enough that there basically wasn't enough ground fuel to sustain that active behavior, and so the fire dropped down onto the ground, which made it possible for firefighters to protect this sort of residential area here in the foreground. All right, so we've got a couple different ways here we can think about visualizing this concept of S, right? The amount of mass flow through our canopy space. One of which is this idea of like Pac-Man, right? He's stationary, and these dots are coming to him at some speed. The dots being the crown fuels, right? And if they're not moving quickly enough, he's not getting dots fast enough, he's not going to be able to sustain himself and won't be able to live, right? So he just needs a certain amount of fuel or Pac-Man food pellets or whatever they are fast enough to sustain him. Oh, we got a little animation here, right? So he's eating his little fuel pellets, and they got to come fast enough. An alternative visualization comes from AG. So we can imagine we've got some forest here sitting on a conveyor belt, and basically as that conveyor belt moves, the trees pass through this theoretical vertical plane. And basically, if trees don't pass through that plane fast enough, if enough fuel doesn't pass through that plane in a certain period of time, then there's not going to be enough energy for that fire to stay up in the crowns and propagate, right? So this is suggesting that there's basically a minimum bulk density, or a combination of a minimum bulk density and a minimum spread rate in order to move that fuel through our plane or through our fire front fast enough to sustain our active behavior. Right, so here's the other part of that image. You can imagine as we kind of cut trees out, all of a sudden, the amount of fuel passing through our vertical plane is drastically reduced, and at a certain point, it's going to be reduced enough that the fire is just not going to be able to stay up in those crowns. So all of this is really just to suggest, right, that there's some certain minimum amount of mass that you need to consume every time step in order for our active crown fire to propagate, right? Therefore, there's some critical value of S, which is going to be independent of moisture content, and it's sort of just going to be a physical property of crown fires, right? There's just some lower limit at which this spread will occur. So looking back at our equation, we'll also see that we can yet again rearrange things basically to put rate of spread now by itself, and we're going to identify rate of spread as a critical value. Basically, the fire is spreading enough, and then we'll basically have enough fuel through the crown space, and it'll be able to propagate. So we now have a new critical value to maybe think about as in terms of rate of spread being critical to maintaining this active behavior. So basically the idea here is that there's some set S0, there's some amount of crown fuel that needs to be consumed per second in order to maintain things, and that value isn't going to change. It doesn't matter what the rate of spread is, it really is just there's some set minimum value of fuel consumption required, right? And basically, further, this suggests that at a given stand, or a given forest has some particular canopy bulk density, and based on the amount of crown fuel that just exists in the stand, there's an associated rate of spread that would be required to sustain an active crown fire through that stand. Right. So if you have a slightly less dense stand, crown fire still may be possible. You just might need it to spread a little bit faster in order to achieve enough fuel being consumed in a given time step to keep that propagation going. Right, and yeah. So basically, with our conveyor belt idea, if we thin those trees out a little bit, we might still be able to maintain our active behavior. We just might need to move that conveyor belt a little bit faster, right? We need to have a greater fire rate of spread to move those trees through our vertical plane fast enough. All right, so hopefully we've gathered that, right, so S0, as I said, is basically a set value, some physical value that, maybe unsurprisingly, once again, Van Wagner sought to use experimental fires to figure out what this actual critical S0 value was. And so based on that same set of experiments we saw in our crown fire initiation talk, Van Wagner was basically able to determine a theoretical S0, or basically the minimum S0 required as 0.5 kilograms per square meter per second. It was basically the bottom value required for active crown fire spread, which leaves us with an equation of R0 equals 0.5 over our bulk density. So R0 being the critical spread rate, the minimum spread rate required for propagation, and right, so these are just our bulk densities. How much fuel do we actually have up there? So just a little backing up to these experiments that he did, right? So we need to estimate S from these field experiments, all really done in pine plantations up in Canada. So here are stand parameters again, stand measurements from those various plantations. And then here is his chart of the fire behavior from the different experiments. Ultimately, Van Wagner used the numbers from red pine plantation R1, basically because that plantation was right on the edge of what he called active crown fire, or he says down on the chart here, developing active crown fire. So it was really just right on that threshold. And so based on the bulk density and the rates of spread in there, he empirically derived this constant of 0.5 kilograms per meter per second, square meter per second. This is pretty close to some lab experiments that were done a little bit before these crown fire experiments. So it seems to be kind of in the ballpark of maybe being some sort of true physical constant that we can work with. A point here to remember, and we saw this with our initiation, is that it's based on a pretty limited data set, right? He used a single red pine plantation to come up with this number. So here's our final model, R0, our critical rate of spread, equals 0.5 over the bulk density. And so just notice here, we're not actually predicting the crown fire rate of spread in this equation. Similar to our initiation, this is really just a criteria for if active crown fire is expected to occur. And if we see on this figure to the right here, basically there are different combinations of canopy bulk density and rate of spread that will allow active crown fire to occur. Right, so basically if our forest is too sparse or our fire is moving too slowly, we're not going to have active crown fire. We could certainly have some pretty aggressive passive crown fire where we're torching out a lot of trees, but if the bulk density isn't high enough, or the rate of spread isn't high enough, right, it's not going to spread from tree to tree up in the canopy, which has a lot of implications for how we might think about the ability to potentially control or suppress that fire, and then particularly how fast that fire is going to move. Because as we'll see in subsequent lectures where we actually want to predict the rate of spread, once active crown fire starts, we're going to be working with a whole new set of equations, and we're going to have much higher spread rates, right? Which come with a lot of risks when we're thinking in terms of either fire suppression, community protection, evacuating people. When our spread rate goes up 3 or 4 times in active crown fire, that has some really big implications, and is just a really important thing to be able to predict. So anyway, we're going to be going there. We're going to be moving towards crown fire rate of spread prediction. But this equation here is all about determining what type of crown fire we have. Do we have a passive crown fire? Do we have an active crown fire? Or maybe we still just have a surface fire, right? That would go back to our initiation equation. Just a couple of quick limitations on here. So we saw there's just one experiment from Red Pine Plantation, but some other work kind of after the fact has shown that it works fairly well in a lot of the northern Canadian forest types, denser, maybe more homogeneous forest types, but a little bit less sure about its ability to predict some of our drier forest types here in the West. It's still proved useful, but right, once you start increasing heterogeneity either horizontally, right, the spatial distribution of trees, or vertically, right, that different mixtures of tree heights, all these things kind of throw a few curveballs in when we're basically assuming, right, homogeneous bulk density and continuous bulk density, right? If there's gaps or areas that have lower bulk densities, that's not really getting captured in here because we're really just using an average kind of stand level bulk density number, which assumes it's distributed equally, which, as we know, is not necessarily the case. So basically these two equations here from Van Wagner 77, his initiation equation we saw in the last lecture, and then his spread criteria in this lecture, really work together to build a framework for what type of fire behavior we expect, right? Whether we expect it to be a surface fire, a passive crown fire, an active crown fire, or even this concept we talked about called independent crown fire. We can kind of estimate all of those things based on just these two equations. Right, so the way it works is essentially first we look at our surface fire, or we look at our surface fire intensity, right? So if our surface fire intensity is less than the critical intensity for torching or transition, well then we're just going to have a surface fire, right? It's not hot enough to burn our trees, or it's not releasing enough energy to ignite our crowns. But if that surface intensity is greater than the initiation, okay, so we're going to get some type of crown fire. So which type? Well, now we look at his rate of spread equation. And so if the true rate of spread is less than the critical rate identified from his rate of spread equation, well, then we're going to have passive crown fire, right? So individual trees are going to torch, groups of trees are going to torch, but we're not going to have that full-on active fire behavior. Then the last step is, okay, well, if our true rate of spread is greater than that calculated critical rate, well, now we've got full-on, fully developed active crown fire behavior. So just visually, this is kind of what it looks like in a chart form. So the lower left quadrant there, right, basically our surface fire intensity has not crossed that initiation threshold, so we have surface fire. And then moving to the right, we now have crossed the initiation intensity and we have passive crown fire, but our rate of spread isn't high enough for it to be active, right? So it's just passive. And then if we increase our rate of spread, we move up into the top right box, right? We've got plenty of surface fire energy, we've got plenty of rate of spread, and so now we've got our active crown fire. And it's actually not on this figure, The authors of this paper don't particularly care for the concept, and it kind of makes sense, but so they don't have it on here, but the top left quadrant there is where we would see that kind of idea of independent crown fire. It's showing that basically the surface fire wouldn't be hot enough to ignite those crowns, but were they to be ignited, a fire could potentially burn through them sort of independently, right? Because there's enough rate of spread and enough fuel for that to occur. Once again, not a super common occurrence. Just another note here, we could also just think about, well, what really is a crown fire? What constitutes a crown fire? And in those equations, or in his spread equation, the assumption is that all of that mass flow is coming from the canopy fuels. And all of that heat flux is coming from, canopy fuels, but in reality, a lot of that heat flux and a lot of that mass flux comes from our surface fire. So the two things are really linked here. But in developing these models, just for simplicity, he's still breaking it up into really the two sort of separate fuel layers. And so, the model is really just, the crown model is really just including the horizontal component, the horizontal flow, but we also could incorporate some vertical flow or the contribution from the surface fire if we wanted to have a little more realism, but some of that kind of gets washed out in the empiricism, so that S0 that he calculated from his experiments, he couldn't actually separate the surface and crown fire. So it actually does kind of get incorporated, if not, explicitly. It's still kind of in there. But anyway, to kind of keep things a little simpler in his equation, he's not really directly addressing that contribution from the surface fire in terms of the horizontal component of the mass and heat flux. So just last couple of notes on this, right? So these models are really the sort of the cornerstone of crown fire behavior modeling in the U.S. And so there are lots of different U.S. fire behavior systems that use these equations. Right? In order to use them, we need some estimates or even measurements, estimates more often than not, but of the canopy level parameters, right? So the bulk density, how much fuel is up there, how large is the space. So we basically need an estimate of the total amount of crown fuel. We need a canopy base height. We also probably need tree heights in order to actually calculate that bulk density. And then we also need to know the fuel moisture content. A lot of times canopy fuels are assumed to have 100% moisture, which is a decent estimation, but there's some data out there to show that changes seasonally, right? That there are certain times a year where there's a little less moisture in the needles, and maybe they're a little bit more flammable, and perhaps we should just kind of be careful to take account for that when it may be important. But anyway, we need some estimate for the fuel moisture. Once again, we're limited by experimentation. So C from the crown fire initiation equation, and then S0 from our crown fire spread criteria equation are both experimental values from a pretty limited range of conditions and experiments, right? So there's some limitation there. And then once again, we've seen this at basically every level of these fire models, that we're not considering spatial heterogeneity in fuels. We're making a lot of simplifications here to really make this possible in a sort of coherent and broadly applicable modeling framework, right? So all these assumptions about the heterogeneity, or rather the fuels being homogeneous, right? Not heterogeneous as they exist in reality. So yeah, just a couple more things to kind of keep into account as we're thinking about using these equations.